Okay. What I'd like to do today is talk about, or finish, Chapter 10 and start in Chapter 11. Before I do that, let me quickly go into several things here under supplemental books. In particular, if you want a fairly complete but a reasonably easy introduction to R, that third one, Learning R, is a fairly good book. It's not free. You can get it at O'Reilly, and the nice thing about it is that if you like, you can get it as an ebook, which you can get it immediately. You notice that if you get the print and the ebook, it's only a little bit more. And the print's almost as much as the print plus the ebook, so there would be little point in just getting the print. They essentially distribute these in almost all formats, in particular PDF and EPUB. So this is a good book to look at. And I think I had already mentioned this book to you, Getting Started with RStudio. It's a little bit dated, although I did see an update, but I don't know to what extent it really was updated. For those of you that want to do reproducible research, this is a very useful book. It talks about RStudio also, but it has a lot of discussion on reproducible research using R, and doing that within the context of RStudio. There's a tremendous advantage of doing this versus using Word, for example. But generally speaking, if you're going to do a publication quality document, you need to do that in LaTeX or LaTeX. But again, that's extremely good research book that you might want to look at also. In terms of the class schedule, things are more or less caught up. I put the Chapter 11 notes. I have some revisions of Chapter 10 notes that I'll be putting up tonight. Most of these notes, particularly starting with Chapter 10, are going to be kind of work in progress. Periodically I may update them with things, and I'll let you know so that you can download the latest version. The Chapter 11 notes are up there. And again, the Chapter 9 assignment is available. I will be putting the Chapter 10 assignment up fairly soon. We'll be finishing it today and starting on 11. So let's go into RStudio. And actually I have Chapter 10 up here. Although I'm not in the right directory. So now I am, and let me set this as the working directory. Okay. And I'll knit it, create the HTML. Let me go up to full screen. Now I'll knit it. Whoops, wrong one. Let me get it, chapter 10. Yeah, I'm set in chapter 10. So just quickly to go over, and I want to show you some of the things I added. We went over the additive model. We could have written this model as y sub I j equals mu sub I plus epsilon sub I j. And if you did it as mu sub I, you would see that there are 8 parameters, mu1, mu2, up to mu a. In the case of our Sol example, it would be mu a, b, c, and d, that is the 4 groups. And we've reparameterized it as mu plus alpha sub I plus epsilon sub I j. The problem is when you do it that way, you have mu, alpha 1, alpha 2, up through alpha a. You have 8 plus 1 parameters. You have what we say over-parameterized the problem. And from the point of view of the matrix algebra that's done internally of Y, you have created a singularity. And you have to remove that singularity in some way. And what I said, what the book does and what JMP does, but not R or SAS, is to set the sum of the alpha sub i's equals 0, and then that removes the singularity. The singularity is reflected in the model matrix, which I showed you briefly last time, and I'll come back to that. Because corresponding to every parameter, there's a column in the model matrix. So if you would just use mu plus alpha sub I, you would have 5 columns in the matrix, and the last 4 columns would add up to the first, and that's why you have a singularity. If we represent that in terms of the parameters, again, we need to do something, and as I said, sort of the classical way of doing something is to talk about a treatment effect as the deviation from the grand mean, and so alpha sub I is defined as the mu sub I minus the mu dot, which is the average of the mu's. Because of that definition, the sum of the alpha sub i's equals 0. What I did here was showed you how to calculate these. This is what we call sort of the internal. The formulas here, the definition makes sense in terms of deviations of means from grand means or observations from sample means. And so we defined it that way, but the computing formula, if in fact you did it by hand, would be these, which are also given as the computing formula. When I did the one-way analysis of variance, I first of all got the means and printed them out, and then I did a box plot. And it's a good idea to do that at the beginning of a study, because visually, side-by-side box plots give you a lot of information. They tell you about skewness, they tell you about outliers, they tell you where the centers are. In this case, the centers of the median. And so this gives a lot of information graphically. And so that's a good idea to do. Now, just to review again, the sum of alpha sub I equals 0. When I did the fit sols, I specified that the contrast would be defined by contrast.sum, and contrast.sum gives the sum of the alpha sub I equals 0. That's not the default. If I would not have had that argument contrast, by default it would have said alpha 1 equal to 0, and that's sort of a global default you get unless you specify otherwise. So if you go back here and you look at the contrast statement, let's see. So let me type in contrast. Let's see. These are the choices. Contrast Hilbert. We'll talk about contrast poly later. That's for orthogonal polynomials. We actually did, and I'm going to show you how you can do more general orthogonal contrast. I'll show you a way you can do it. But if you're doing orthogonal polynomials, what you would do if you sort of have treatments, if you have sort of the quantity of a fertilizer and it's 10, 20, 30, 40, that's sort of a numerical scale because you're talking about the amount of fertilizer, let's say. And so if you did 10, 20, 30, 40, we could actually fit a linear, quadratic, and cubic. And we could do this using what are called orthogonal polynomials. So we could get an idea of whether or not the response to the fertilizer level is linear or quadratic or cubic. And by defining them as orthogonal polynomials, it defines those contrasts to be orthogonal to each other. And so there'll be an example of that later. The contrast sum is the sum of the alphas of I equals 0, which is what I used in order to conform it to the book. The default is contrast dot treatment. Now, notice it says base equals 1. That's the default, and that is, in fact, the global default. If you don't do anything in R, it does it with contrast dot treatment, and it uses base equals 1. Now, if I said base equals 2, it would actually set alpha 2 equals 0. And you might want to do that if, in fact, let's say the second level is a control. If you wanted to compare everything to control, then you could set alpha equals 2. You could also set alpha equals the last, but the problem is you don't know which one the last is. That is, you don't know what A is. You don't know how many levels you have. I mean, you could compute it, but it turns out that contrast.SAS sets the last level to 0. That's what SAS does by default. It sets the last level to 0. So there you've got it. R sets the first one to 0 by default, SAS sets the last one to 0, and jump does the sum of the alphas of I equals 0. None of them agree. And that makes it confusing to students. You know, you might learn it on jump, and then you use R, or vice versa, and you say, what's going on? It turns out that the F-test and the T-test don't depend upon which you choose. The predicted values and the residuals don't depend on what you choose. I'll sort of try to geometrically show you what's going on. And you'll see that, well, you might see, depending on your geometric intuition. So going back again, we've already gone through this. When I get to the point that we're doing something different, I'll go back to the other, the other slide. If I'm doing the overall test, once I get fit-sols, and I get fit-sols from an LM, so using LM. Now, by the way, there is a function called AOV. And you may wonder why I don't use it. Well, the reason I don't is because it assumes a balanced design. In other words, it assumes that the n sub i's are equal. And this even becomes more important once you get to a two-way or three-way analysis of variance. In that case, you feel free to use AOV as a function. It works the same way. It's just that it assumes balance, and we often don't have balance. And so, from my point of view, I don't spend a lot of effort on the AOV. But there is a function called ANOVA. Once you create the object, that is, once you create, in this case I called it fit-sols, that's the output from LM. There are several things I can do. First of all, I said contrast of model. Now, model doesn't mean the model. It's actually the treatment. In other words, the model or chainsaw. So I have angle tilde model on the right-hand side of the tilde. So I'm modeling angle as a function of model, which is a factor. When I say contrast of model, that shows the contrast. In other words, you can see for A, the first column, it's set to all zeros, and then B has a 1, C has a 1 in the C position, and so forth. So that is the contrast matrix that's created. And then I do ANOVA of fit-sols, which is the LM object, and it gives me an AOV table. And so that's good. We see that we have a significant difference. But if that's all we did, it wouldn't provide you much information in terms of what's really significantly different from what else. And so we need to look at that a little more carefully. So we have a significance. Now, there's another example here where we have, this is doing it to a psychologist, and we have behavior disorders. And so this is just a little bit of the data. There are actually 7 disorders, and you can see in this case that the sample sizes are quite unequal. But here we fit it, and again I'm going to use the contrast sum. Now, by the way, you can change the global default. There's an options function in R which has options that are globally defined for lots of things, including contrast. So you could, if you always wanted the sum of the alpha spy equals 0, always, you wanted to look like jump, you can set that to be true at the global level. It's just by default, it's using contrast treatment. So there is a global function called options that lets you change it globally, so it would always be true. And by the way, there's a startup script you can also run, and you could put that global change in your startup script, so every time you launch R, you in fact just look like jump. Or if you want to look like SAS, you could set the SAS option. So R is quite flexible. I don't think jump actually lets you change the contrast. I mean, it's what it is, and that's it. And SAS might be that way. I'm not sure about SAS. Now, if we get to multiple comparisons, I said that we can take some linear combination of the sample means, and we can test whether or not. In other words, if you consider that, we can look at the sum of the C sub i's mu sub i's equals 0, and for any arbitrary C sub I, and we actually can get a t-test for that. And we just have to get, if we had the sum of the C sub i's y bar sub i's, which is the sample antilog of the sum of the C sub I mu sub i's, then all we need is the standard error. And that's actually very easy to compute. It's just the pooled, it's the square root of the error mean square, that is what we call S sub t, the pooled error mean square. And then times the square root of the sum of C sub I squared over n sub I. So that's easy to do, and we could do that for any set of C sub i's. But the problem is if you do a bunch of those, then you start inflating, you start rejecting too many times, because if you're testing each one of those at the 5% level, once you do a bunch of them, you're going to find some of them significant just by chance. So typically what we do are 2 things. We either do one of 2 things. We want to limit the number of contrasts we look at. Now, the exception is Chaffee's method. Chaffee's method lets you sort of play to your heart's content. The problem is it's very, very conservative. That means it's very hard to reject. So you pay a price by using Chaffee's method. I presented Chaffee's method such that you're doing just pairwise contrast. But in fact, you can do any contrast with Chaffee's method. You can do it to your heart's content. You just won't find much significant because it's so conservative. And so it lets you play around in the sandbox, but that's one place you can play around in the sandbox and not worry about your family-wise error rate. But again, it's very conservative. So these are not particularly of interest. What's more of interest is to define either orthogonal contrast or pairwise contrast, and I'm going to talk about those. So we had Fisher's LSD, and we did that with the pairwise.t.test. And it turns out that it appears that there's some very general methodology that it's using to do this. And for example, the Student-Newman-Cools, you could actually use the structure with the pairwise.t.test, or you could use not that per se, but there's something called pairwise.tables or pairwise.table. And that pairwise.table is what gives you that little table of the p-values, which I'll show you in a minute. So you could actually build up, and I've added a little bit on Student-Newman-Cools. It turns out that there is a function called p-Tukey that lets you compute these, and right here I wrote it. The Q is the difference divided by it's called a studentized range. And what it does is it takes differences and divides by the square root of the mean square error divided by, I have n tilde, which is the harmonic mean. Now, it turns out that the harmonic mean is equal to, if the sample sizes are all the same, n sub I equals n for all I, then it turns out that the harmonic mean n tilde is in fact n. You can see that easily by looking at the definition. So again, what I said is that as long as the sample sizes are almost equal, you're okay. Now, if you go look at Wikipedia, they have a mistake. They actually have a standard error that's sort of 1 over n sub I plus 1 over n sub j, even if the n's aren't equal. That's not correct. I haven't looked what they did for Tukey, but Tukey is sort of an extreme case of the studentized ranges. So again, I haven't put a focus on that, and I totally skipped Duncan's new multiple range test. The reason I skipped it is because no one does that anymore. There's a lot of other alternative procedures that are used instead. Now, Tukey's is certainly used, but I would argue it's just sort of the extreme case with the maximum range. If you note, you probably can't see it, but there's a little r in this Q. That critical value I look up, and there's a Q table in the book, and also you can compute these Q's from the function. Well, there's a P Tukey which computes that would compute the significance levels, but there's also a Q Tukey which would actually calculate those Q values there. So we could compute them, and I didn't do it here yet. I may put it in at some point. You could compute that Q value, and you actually could carry out the test exactly like they are in the book, and then you could eliminate the table in the back of the book because R does it. But the point is that I didn't put a lot of emphasis on student Newman Cools, but it is kind of a stepping stone between the more liberal Fisher's LSD and the more conservative Tukey's HSD. Now, as I said, Tukey's HSD, there is a built-in function for it, and that called Tukey's HSD, and it uses that same Q, except that it uses the maximum. That R value becomes A, which is the maximum range. The idea is this: I rank the means from smallest to largest. And in Tukey's, I look at that maximum difference, which is a difference from the smallest to largest. There are A of these, so that A parameter comes from comparing the smallest to the largest. And it looks at that adjusted studentized range, which is that Q value I defined up here. But on the other hand, if I'm comparing the ones that are 2 apart, in that case, in case R would be 2. If I compare 3 apart, then R would be 3, and so forth. And what happens is that Q value gets bigger as that R gets bigger. And so if R equals A, it's the biggest. And that's why it's most conservative, because all pairs are compared to that maximum Q value, that quantile. And so therefore, it's harder to reject. And that's also why you know, it's kind of a nice intermediate position between Tukey's and Fisher's LSD, and it's sort of in a continuum. But it does involve special tables, but I hadn't realized till I sort of looked around that there's a function called P Tukey, which computes like the P values, and then there's a Q Tukey, which computes the quantiles. By quantiles, I mean this quantity right here. That's a quantile right there. So you can actually compute both of those. So in principle, we could do it. We could replicate what's in the book. I just haven't done it yet. Replicating that is one thing, but writing the code that would create something like this table, not that table. Where is it? Oh, down here. Remember all these little tables that have the p-values in it? That table. That's slightly more difficult. But again, I found this function called, I think it's called pwise.table, and that facilitates you computing those tables. So in principle, I could write some code that would take student Newman Cools or Tukey's, and presented in that same type of table as you have here. But it would take some programming. Maybe over a fall break I'll do that. So. At any rate, going back, again, what we're trying to do is to control the overall alpha error rate. And so technically all three of these do. Fish's LSD, the way it really does it is sort of what you call a voluntary compliance. Why do I say voluntary compliance? Because you do your overall F test for the overall significance. And that F test, by the way, if you don't know about the F test, that's talked about earlier in the book. And so the F test, is the ratio of two mean squares, both of which are distributed as independent chi-squares. And there are 2 degrees of freedom for the numerator and denominator. And this F test is a skewed distribution that starts at 0. So we only reject in the upper tail. And we'll talk a little bit more intuition about in the next chapter about the F test. But at any rate, the F test is an overall test. And if you say, okay, if I reject, I'm going to go ahead and do multiple comparisons with Fish's LSD, then you've been protected as long as you say, if I don't reject, I do nothing. Now that's the problem. Very few people have the discipline to do nothing. They just kind of want to look at it anyway. And so it's the overall F test that protects you with the LSD. So if you go ahead and do it, even if you didn't reject, then you no longer have a family-wise error rate of 0.05. And so technically you're protected. It's just that most people sort of want to look at the multiple comparisons no matter what. And so therefore we've developed these other procedures that sort of protect you against yourself. And the Student-Newman-Cools and the Tukeys are 2 fairly effective ways to do it. But as I said, you get more and more conservative as you go along. So I don't have the actual code in here, but in principle I could develop it. I mean, it would be easy for me to give you what the particular quantiles are, and by taking differences you could easily sort of figure out which ones are significant or not. But to make it nice would take more programming. Chaffee's method with this F value here I didn't do. And by the way, one problem again with Student-Newman-Cools and Tukeys is that they do require equal sample sizes, or somewhat unequal but not too unequal. If it's unequal, you can use the harmonic mean again, as long as it's not too unequal. But you start getting bias if the n sub i's are too different from one another. So these 2 procedures are nice, but if the sample sizes are widely different, I wouldn't recommend them. Chaffee's you can use, again, it's like Fish's LSD. If the n sub i's are unequal, that's fine. You can compute the pairwise differences this way. And in fact, you can actually compute any contrast, any sum of the C sub i's, mu sub i's that you're interested in. And you're still protected, but it's very conservative. So I didn't actually write out the code for that, but again, I don't know that there's a function built into R that does this, but it wouldn't be too difficult. If you were interested in a particular set of contrasts, you could actually write some R code to do it. Are there any questions on that? Well, we talked about the one-way. We talked about the orthogonal contrast, but I've added some code on how you do this. So in the book, you remember the sol example. Suppose you have sols A, B, C, D. Those are the model types. And suppose A and D are lightweight or home use sols, and B and C are commercial sols. Okay? So A and D are home use, B and C are commercial. And so if you then said, well, I'd like to define some orthogonal contrast. What would you define? Well, you'd probably define home use versus industrial use. So you'd have A and D versus B and C. Then I could also construct, a contrast of the A versus D, which is comparing the two commercials, and B versus C, A versus D, which compares the two homes use, and then B versus C, which compares the two commercials. Okay? And I claim that those three would be orthogonal, and that's what I want to show you. So what I'm first of all defining, I'm defining a contrast matrix called CNTR.orthog. That's my version of CNTR.orthog. I'm going to combine the three sets of contrast. Now, here's the first one. The first one is, here's the first contrast is right here. Now, what is that? That's 0.5 minus 0.5. Well, you can't see the minus, maybe. There's a minus sign right there. Is that visible at all? If you look carefully. There's 0.5, minus 0.5, minus 0.5, and 0.5. Now, notice, first of all, the sum of the C sub i's equals 0, right? It's a contrast. So we have minus 0.5, and we have 0.5, minus 0.5, minus 5, and then 0.5. That compares A and D versus B and C. Now the next one is 1, 0, 0, minus 1. What does that compare? That compares A to D, right? Because I got 0, 0. It zeroes out B and C. So it's just comparing a plus 1 for A and a minus 1 for D. So it's comparing, remember we're taking the sum of the C sub i's, mu sub i. So it's comparing mu1 to mu4, or mu A in this case to mu D. And then the next one is 0, 1, minus 1, 0. That's comparing B to C. Now I also, and here I printed them out. Now I claim that those are orthogonal. What was the condition for orthogonality? It was the sum of the cross products equals 0. So let's take I labeled these L1 and L2. Let's take L1 and L2. If I take the cross products and add them up, is it 0? So what is the cross product? It's 0.5 times 1 plus minus 0.5 times 0 plus minus 0.5 times 0 plus 0.5 times minus 1. Now the two middle ones zero out, right? So the top one is 0.5 times 1, which is 0.5, and the bottom one is 0.5 times minus 1, which is minus 0.5. The sum of those is 0. So L1 and L2 are orthogonal. But also it's clear that L1 and L3 are 0. So if I multiply 0.5 times 0 plus minus 0.5 times 1 times minus 0.5 times minus 1 times 0.5 times 0, again, the sum of those is 0. And also 2 versus 3 is 0, because you have 0 times 0, 0 times 0, 0 times minus 1, and minus 1 times 0. So those three, L1, L2, and L3, are orthogonal contrast. Okay, fine. So how do we fit? You know, that's great. We've defined a R variable called contrast.orthog. So how do we actually partition the sum of squares into 1 degree of freedom contrast, and how do we test that those contrasts are significant or not? Now you may recall from the graph that here A and D are the home use, and they appear to have less kickback than the industrial ones, which are B and C. So is there a difference? So in other words, does A and B collectively, A and D differ from B and C, and does A differ from D, and does B differ from C? You see, those medians appear to be different, although, you know, A and C are the low ones, and B and C are the high ones. But there's still some differences, but there's also a lot of variability, and we don't have a very big sample size. So let's sort of see what happens. So I say contrast of model. I say contrast of model gets that matrix. And then I fit the model LM angled tilde model. And when I do that, it's going to use that contrast matrix that I've just defined that's orthogonal. And if you want to see why that's true, then print out what's called the model matrix. I talked about the model matrix a little bit last time. And I talked about it in section 5 when I was talking about estimating some mean differences, and I was talking about the difference between setting the sum of the alpha size at 0 versus setting alpha 1 equals 0. And so we'll come back to that. But if you print out the model matrix, now what I did is, this code may confuse you a little bit, but here's the model matrix right here. I'm taking LM and I'm extracting the model matrix from model.lm. And model.lm is the fitted model with this set of contrast, and which are orthogonal. And then I say as.data.frame, I coerce it to a data frame, and then I put the names. I put I for the intercept, and then L1, L2, and L3 are those three contrasts I just defined. So that's the model matrix. Now you see the first column are all ones, which fits the intercept. And then notice I have the 0.5s, the minus 0.5s, the minus 0.5s, and the 0.5s for L1. That's the first contrast. The first 5 observations are in the first group, so they get a plus 0.5. The next 5 observations are B, and they get the minus 0.5. And then the next group, the next 5 are C, and they get the minus 0.5, and the last group gets 0.5. And then L2, notice the first group is 1, then 0, 0 for the next 2 groups, and then the last group is a minus 1. So this is sort of a stretched out version. This is sort of a stretched out version of this matrix up here. In other words, one of these for each observation in A and B and C and so forth. So instead of having 4, I actually have 4 times 5 or 20. So that's sort of the last 3 columns are a stretched out version of that, one for every observation, as is appropriate, whether it's A, B, C, or D. That's all that is. Okay. Now notice, I can run this in just a little bit, but notice that I now do an ANOVA table, and I'm fitting the model. Notice I attach L, which means I can access these names. In other words, if you would just type in L2 in the model, in the workspace, and I'll show you in a minute, in the workspace, it knows about L, but it doesn't know the column headings of L until I attach it. And once I attach it, it knows the column headings. So I'm going to fit a model I plus L1 plus L2 plus L3. And what it does is, this gives me analysis variance table where it gives me sums of squares. And I'll notice these sums of squares, and I want you to contrast it with this sums of squares, which is the ANOVA for model.lm. Model.lm has 1080 as the sum of squares for the treatment. And notice that it's significant. So I want you to sum up these 3 sums of squares that have 1 degree of freedom. The 980 plus 10 plus 90. What does that equal? It's equal to 1080. In other words, what I did is I took that sum of squares and I partitioned it into a sum of squares due to L1, L2, and L3. And since they're orthogonal, it will add up to the total sum of squares. So this let me test exactly what I wanted to. I wanted to compare the industrial. I wanted to compare the industrial to the home use, and so forth. Now notice that the only one that's significant is comparing industrial to home use, and it's significant at a fairly low p-value, 0.0067. So that's highly significant. Whereas the other two, comparing A to D, which is the home use comparisons, is not significant, nor is B to C. So the only thing that's significant here is comparing the home use to the industrial. Okay. So if I step through this and let's see, I got to be careful where I do this. Sometimes it's a little bit hard to find some orthogonal contrast. Yeah. So if I look at the workspace here and if I do the orthogonal comparisons, so first of all I define that, and then I define the rows to be the first 4 letters. In other words, letters 1 to 4 of capital L-E-T, all caps and letters gives you A, B, C, D, E, F, G, and the first 4 is A, B, C, D. I was just trying to get an easy way to get A, B, C, D. I could have written it as C, A in quotes, comma, B in quotes, comma, C in quotes, comma, D in quotes. I could have done it that way. And then the column names, I'm going to name, I did do the column names that way. I used C, I just called the contrast L1, L2, and L3. Notice they're in quotes. And then when I print out the matrix, so let me do that also. And then when I print out the matrix, you would not have had those column and row names had I not named them. So I used a function called row names and column names, which you can use on arrays or matrices. And that just made it look nicer, but it was more work. Okay. So going down here, let me see. I've got to someplace. Where do I do the model? Do I not do it down here? What I have to do is go all the way back up here, and I have to read in. In other words, I haven't read in the data yet, so I have to read in the data or it won't find it. So if I do this, and then attach solves. Okay. I'm not okay. Should be defined, yeah. Okay. So I now have solves in there, and going back to, so now if I define the contrast for model, this is what's called a replacement function. It's taking model, which is on the right-hand side after the tilde. In other words, I'm fitting angle tilde model, and I'm defining the contrast of model to be contrast.orthog. Otherwise, by default, it's going to use alpha 1 equals 0, and it's not what you want. And now I'm going to fit the model, and then I'm going to do with this coercion. Now, if I do a model dot, well, I don't really need to do it because again, I'm getting a model matrix. I'm coercing it at a data frame, and I'm going to, again, I have to, if I just type out model dot matrix, if I type out model dot matrix of model dot lm, let's see if I would spell it correctly. It prints out this. It also prints out this additional information. These are called attributes. In other words, the model matrix is precisely what I'm going to print out. it gives these same values that I defined as L when I coerced it to a data frame. But it also gives the attributes, and it gives the attributes, in particular the important one is that the attributes is this contrast, these contrast, which I had defined. Okay. Now notice that the names are model L1, model L2, and model L3. That was default, and then it gives intercept in parentheses, which is not really the name. If you try to use that as a name, it will not work. So I'm going to define new names for this data frame. I coerced that model.matrix to a data frame L, and then I'm going to give it new names. And now when I print it out, it prints out a little nicer, and it doesn't give all those attributes. Okay. I think I had already attached L, but if I had not, I'll do it. Now if I do an ANOVA on this, you know, I get this breakdown, and then if I do it on the model.lm, and again, this is where I said that sum is equal to the sum of these three under the sum of squares. So I partition the sum of squares into three parts such that they add up. I have 3 degrees. Notice I have 3 degrees of freedom. That means I can define 3 orthogonal contrasts such that the sum of squares will add up. That's not the only way I can define orthogonal contrast. It's just the way that I did it because I was interested. A priori, before I ever did the experiment, I knew I wanted to, say, compare industrial sols to home use sols. And so a priori, I knew I wanted to do these comparisons. So I'm allowed to do 3 of these that are orthogonal. If I do more than that, I get into this singularity problem. If I do a fourth contrast and try to put it in there, it would be 4 degrees of freedom. I would get a singularity. So I could only do, in other words, I did I for the intercept plus L1 plus L2 plus L3. If I would have had an L4 in there, you would have a singularity. Okay, are there any questions on this? So that's how you can do it in R. It's I think I showed you last time how to do it in JUMP by those pluses and minuses you can click on. So you could define, in JUMP, you can define those orthogonal contrasts a little more easily than you can here. But again, once you sort of see, I put some extra steps in here that you didn't need to do. You know, you don't really, the only thing you really need to do is do the contrast matrix and then use it. But if you then want to break out the single degrees of freedom, that's a little bit trickier. But you don't actually need to do it that way because instead of using the ANOVA function, you can use the summary function, which breaks out the degrees of freedom. So, in other words, if I type in here summary of, what did I call it, model.lm, you see that uses the model L1, L2, and L3. That also, these tests are exactly the same here as I got up here. The only reason I did what I was showing you that in the way you can get the sum of squares to add up, I can break and the book does this, you can break the analysis of variance table into the single degree of freedom contrast. But if you're really just interested in a test, all those statements I did, I can reduce to a couple. Because all you really need to do is to define the contrast matrix, which is one statement, and then you need to use that contrast replacement function to put that in for model, and then that's all you really need to do. You can run the ANOVA to get the overall, and then you can run the summary of that, and you'll get that. And that's really all you have to do. So you only need 2 statements. You need the contrast matrix defined, and I define that. So I need the only thing I really need to do, if I'm only interested in testing, is this statement right here where I define this, and then the only other thing that I need is this statement. So those are the only 2 I really need. And then I could run LM on angle, and then I can do an ANOVA and get the overall, and then I could do the summary of model.lm. And I do those anyway, because usually I do the ANOVA function and the summary function. And so you really only need 2 statements, I simply did extra ones to show you how you reproduce what's in the book, although the book doesn't actually have it for this example. They have it for another example. Okay, any questions? Okay, when we got to estimation, one of the key things that I wanted, I'm going to go back and do the, see, where do they define fit solves? Sometimes it's hard to find these. It's got to be here. His fit solves. Contrast. Oh, here it is. I'm going to go back up here, and I'm going to do this particular run right here. So there's fit solves. And notice that if I do the ANOVA on fit solves, this particular table right here with that 1080, using those contrasts, at this point, this is using the contrast. The fit solves is using the sum of the alpha psi equals 0 as the contrast matrix. And it gives you the ANOVA table is exactly the same. Now, the summary table is different because the summary table breaks it into degrees of freedom depending upon how you parameterize the problem. So if I parameterize it with L1, L2, and L3, it gives me a summary table with that parameterization. If I parameterize it with sum of the alpha psi equals 0, then the summary gives that breakout and so forth. So the summary gives the breakout. The summary tables are different because they break them into degrees of freedom according to the contrast matrix, whereas the ANOVA is not different because it's doing the overall, and that's always the same. Okay, I know it's a little confusing, but you need to think about it, and particularly, you wouldn't have had to think about it quite so much if everyone agreed to the convention that the sum of the set alpha psi equals 0 is what we're going to use, and all the software packages use this, then this would be less of an issue. But unfortunately, that's not the case. And so it's ironic that all three major systems use something different, but they did. So at any rate, let's go down to section 5 again. And I wanted just to, still not down to section 5. Yeah, what I wanted to show you that I can get this summary function, which is now going to break it out, assuming that the sum of the alpha psi equals 0. And so notice that if I take the 39, which estimates the intercept, and then alpha hat 1 is estimated as minus 6, so mu plus alpha 1, the hats on those, will be the first mean, y bar 1. And so 39 plus minus 6 is 33, which is the first mean. 39 plus 4 is y bar 2, which is the second mean. 39 plus 10 is 49, which is the third mean. So what's the fourth mean? There is a fourth one, right? Remember, if the sum of the alpha subis is equal to 0, then alpha 4 equals what? It equals minus 1 plus minus 2 alpha, minus alpha 1 hat minus alpha 2 hat plus minus alpha 3 hat. So if I take the sum of those, the minus 6 plus 4 plus 10, that's 14 minus 6 is 8. But it's minus 8 because it's minus those, so it's 39 minus 8, and the first mean is 31. That's how you get it. Okay, that's how you get it under the assumption that the sum of the alpha subis equals 0. Okay, and again, here are the model means, and you can sort of verify, where did I compute model? Model means is something I computed previously, but take my word for it. It's, it's equal to 33, 43, 49, and 31. I hadn't recomputed that. That was way up at the beginning where I computed the model means. Now, what I'm showing here, if you look, here, I'm computing the estimate of sigma hat. And I get that from the summary statistic. In other words, I have fit.sols and sum.sols. The fit.sols, and I've talked about this before, the fit.sols is the fitted LM object, where sum.sols was what I defined. Again, that was my definition. What I define as the summary output. So the summary.sols is defined right here. And, you know, I showed you that you get different things, you can extract different, these are the things you can extract from the fit.sols, and these are the things from the summary.sols. So if I want sigma, I have to extract it from the sum.sols. It's not in the fit.sols. Okay, and so so what I'm doing here is I'm getting sigma hat, which if I want an estimate from it, that's the estimate for sigma hat. Okay, and if you go up here, you see this value right here, the residual standard error. That's what it is. In other words, in the analysis of variance table, well, in the summary table, this residual standard error right here is precisely what I just pulled out. Now, if I wanted to compute, say, the standard error, let's say I want the standard errors of the alpha hats, then that's the square root of the mean square error times big N, the total sample size, minus n sub I over n sub I times big N. So big N is 20, and all the little n's are 5. So the numerator is 20 minus 5, or 15. The denominator is 5 times 20, or 100. So that's 15 over 100, times the square root of that, which is that sigma estimate. That is the square root. So it's roughly 10 times the square root of 15 over 100. So that's actually what I'm computing down here. In other words, I'm computing this, and so that's the standard error for the alpha hat sub i's. And so if I compute that, where is it? Sometimes it's hard to find. Yeah. This is the standard error right here, 3.89. Where is that in the AOV table? Well, that's all these. These three right here. They're all the same because the sample size is equal. So in other words, I'm testing the alpha sub i's equals 0 here. And those are the standard errors. And I just showed you how to compute that. I could have shown you how to compute, could have shown you how to compute any one of these quantities. Now, the most important thing is the mu sub I. Those are the pairwise contrast, which, as you know, is the square root of the mean square error times 1 over n sub I plus 1 over n sub j. And so those are the pairwise differences, and that's the most important thing. And the last one is also important. Those are those general contrasts, which we did some of those when we defined the orthogonal polynomials. Not orthogonal, the orthogonal contrast. So at any rate, I just wanted to show you a few other things. Now, what would happen if you use R? And if you use R, this is the model matrix. Remember what I showed you a model matrix for L1, L2, and L3. This is the model matrix when you use the standard. I'm sorry, this is the sum of the alpha sub I equals 0. The fit-sols uses that, and so that's what the contrast matrix looks like. It has 1s, 1s, and 1s sort of down the diagonal, and then it's got minus 1s, and that's because alpha 4 is equal to minus alpha hat 1, minus alpha hat 2, minus alpha hat 3. So that's why those minus signs come in. So that defines that last effect. And then what I'm showing you, again, I went through this last time, but I wanted to show you This is what R does. Here I'm sort of refitting. I'm doing Fitzell's 2, which was what I did when I used the contrast. And this is a mistake in the notes because I haven't put this up there yet, and it's by default using it didn't change the L1, L2, and L3, and so the notes are wrong right now. But this will correct it, and I'll put it up. This is what R does. That's the model matrix setting alpha 1 equals 0. Notice that for the first 5 observations, the last 3 columns are 0, 0, 0. And then for the 6th observation, there's a mu plus alpha 1. And then the next 5 are mu plus alpha 1. And then the next group of 5 is mu plus alpha 2. And then the last group is mu plus alpha 3. Is that clear what's happening there? That's what R does by default. I've shown you one additional thing, and that is how SAS does it. This is the way SAS does it. And here's the code for doing the SAS. I said contrast equals list model equals contrast.SAS, and then I do the model matrix. And here, alpha 1 is not 0. In other words, it's mu plus alpha 1 and so forth, mu plus alpha 2, mu plus alpha 3. And then notice it's got the 0, 0, 0s for the last group. And so that last group actually estimates y bar. And then I have, it's sort of similar to the way R did it. So I know this is a little bit confusing, and I apologize for it, but when I'm doing contrast, when I'm doing test, it really doesn't make too much difference. But if you start defining your own contrast, then it does make a difference. Okay, taking a little longer than I thought to go through this. Well, we had these procedures in which we found out when we did multiple comparisons that Tukey's is quite conservative, and Tukey's corresponds to a family-wise error rate. So the question is, what do I mean by a family-wise error rate? So let me first of all, let's look at this matrix right here. Across the top, it says, in the first column says that H0 is true. The second one, HA, the alternative, is true. And then the rows will be significant and non-significant. So let's look at, there are 4 cells, V, S, U, and T. So let's look at V. What is V? V are the number of times that I reject the null hypothesis when in fact the null is true. So the column says H0 is true, and the conclusion is that you say it's significant. So V are the number of false positives. You say it's significant, it's not. Okay, so V is the number of false positives, which we call the type 1 errors. So those are the type 1 errors. Okay, then what is S? S says the alternative is true, and you say it's true. You want that to happen, right? In other words, S will be the number of true positives. And now, what is U? U is the number of true negatives. In other words, in fact, the null is true, and we say it's not significant, which we conclude it's true. So U is good. If the null is true, we want to say we don't want to reject, right? And so those are the number of true negatives. Now T are the number of false negatives. In other words, those are the type 2 errors. That's when the alternative is true, but you say that it's not significant. That is, you accept a null. So your mistakes are V and T. V is the number of false positives, and T is the number of false negatives. Now V plus S will be R, which is total number of significant you find. And let's say you do M, small m contrast. So if we're doing all pairwise comparisons, and we have 4 groups, we have 4 things taken 2 at a time, right? Which is 4 times 3 over 2, or 6. So we have 6 comparisons in our chainsaw example. But on the psychology disorder one, how many do we have? Well, we had 7 treatments, so we had 7 things taken 2 at a time, which is 7 times 6 over 2, right? Or 21. And so there you start having, even with 7 treatments, you start having a lot. Now the problem is, if you're doing a genomic experiment, you might in fact do thousands of these comparisons. And so if you don't control the error rate, you have a problem. Well, what are you doing with the family-wise error rate? You're trying to control it in such a rate that you control the probability that v is greater than or equal to 1. Okay? So the family-wise error rate, FWER abbreviated, is equal to the probability that v is greater than or equal to 1, or 1 minus the probability of v equals 0. And I want that to be less than or equal to some global alpha, some alpha sub g, let's say 0.05. So I'm going to set a global alpha, say 0.05, and I want the probability that I get at least one false rejection or type 1 error, a false positive, or type 1 error. I want that to be controlled. Okay, so these various procedures, one way to do this, Bonferroni. What Bonferroni simply does is it said that if I want alpha sub g, the global, to be, if I want it to be controlled at say 0.05, and I'm doing m tests, that means I'm going to take each test to be alpha sub g, the global one, divided by m. And you can show that as an approximation that in general, alpha sub g would be, if you just did 0.5 on all your 6 tests or whatever, then it would be 1 minus 0.95 to the mth. And so if you were just doing 6 tests, then your global alpha level is actually 0.265, which is very big. In other words, the probability I find, that's 1 minus 0.95 to m is 1 minus v equals 0. The probability of v equals 0. And so you can see that the global error gets totally out of control very quickly. Now, Bonferroni simply says divide the global by m. The problem if m is big, it becomes extremely conservative. Now, so various people have tried to correct this, and one of the common methods is Holmes methods. It's called Holmes step-down method, and I can show you how you compute those adjusted p-values. But the pairwise.t test actually lets you do Holmes method, and it's first of all, it's as powerful as Bonferroni. I mean, it's how do I say? It's uniformly better than Bonferroni, so that there would be no reason really to use Bonferroni. You use Holmes as an alternative to it, and it's more powerful than Bonferroni. It means you're more likely to find the differences you want to find, and it still controls the family-wise error rate at 0.05. So there would be almost no reason to use Bonferroni. Now, that's a step-down procedure, and I may show you a little bit more about this next time. There's a step-up procedure called Hochberg's, and that step-up procedure is actually more powerful than Holmes' procedure, except for the fact it means you're more likely to find differences, but it has more assumptions. So if you feel like the assumptions are correct, then that would be the way to go. Now, the problem is these family-wise error rates, even with the Holmes and the Hochbergs, even with these two, they are still fairly conservative. And genomics, people got into genomics where you're doing lots of gene expressions and you got lots of genes, you want to do comparisons, and it turned out that you weren't finding genes that people thought were really significant. And so people started looking for alternatives to this, and they came up with a term called the false discovery rate. Now, I mentioned these two, the family-wise error rate, false discovery. There are a lot of other ways of doing this. If you actually Google multiple comparison procedures, you'll find all these different classes of ones. But the two main ones are the family-wise error rate and false discovery rate. And I'll just mention the false discovery rate. If I take V over R, remember V is what we don't want. R is a total number of significance, and V, I'm looking at the proportion of false significances over the total number of significance. And I want the expected value. I want to look at the expected value, which is the false discovery rate. I want to control it. I want the expected value of that to be reasonably small. And there are two procedures I'm going to mention here, which I can't pronounce the names particularly well. But the Benjamenti and the The Benjamin and Hotspur I can pronounce, but sort of. Again, that's called the BH method, and again, that's more liberal than the family-wise error rates, and that's a fairly nice procedure. There's another one that's actually even a little bit more liberal, if in fact it controls for what are called positive dependencies, whereas the first one assumes independence of the comparisons. And so the BY in the end is perhaps one of the ones you may want to use if you have a lot of comparisons. So I'll stop there, and I may put a few things, before I put this new setup on the notes, I may give you, at least for the Holmes case, how you compute those adjusted P's, just so you get the idea of how it works. But basically, at some point tonight, I'll put Chapter 10 back up with some of the material that there's some additional things, plus there's some corrections, a couple of corrections. Okay, so we are actually essentially finished Chapter 10, and on Wednesday we'll be looking at Chapter 11. So read Chapter 11.